In this tutorial, we will be measuring bit error rate. There are 4 parts: a transmitter, a channel where we will add band-limited noise, a receiver, and instrumentation. For this experiment, we are using Emona TIMS 301C equipment. The top half of the equipment is slots for the different TIMS modules, which represent blocks in block diagrams. The bottom half of the equipment contains, among other things, a frequency counter, master signal section including 100 kHz carrier, bit clocks, and low frequency signals, and outputs to the oscilloscope, which we'll also be using. On top, we have a Tektronix 4-channel oscilloscope, which is a separate piece of equipment. Here we have a poster specific to this experiment for bit error rate measurement. The poster outlines the experiment and clearly shows how the modules are patched to each other. We will first model the transmitter. This consists of 2 modules, a sequence generator and a line code encoder. Inputs are on the left, outputs on the right. All chips are sockets for easy repair. Red sockets are digital and yellow are analog. These we will put into the first 2 slots on the top half of TIMS, although any modules can be put into any slot. Each module is also hot swappable and fully overload protected. They are patched like so, or you can look at the poster for this experiment. The second part is the channel, which begins with an adder module, then a noise generator where noise can be added in 2 decibel steps, and finally a baseband channel filters module. These are then put into the slots next to the transmitter section, but with 1 slot in between for organization and convenience to keep the sections of the experiment separate. They are then patched this way, or you may look at the poster. The third section is the receiver, which consists of the decision maker and line code decoder modules. For this experiment, we have used biphase Manchester as the encoding option for the signal, but TIMS has many other options available as well. Besides the inputs/outputs for the line code encoder and decoder modules, there is also a switch on the back of the decision maker, which must be set to the right encoding option. Turn the switch to biphase Manchester, or whichever option you are using. You can now see the receiver modules patched up and in place, 1 space away from the channel section, again for convenience. Finally, the instrumentation section, which consists of 2 modules, another sequence generator, and the error counter utilities module. We have now completed all patching for this experiment except for the outputs to the oscilloscope. The first output is from the bottom X output of the first sequence generator. The second output is from the in1 input of the decision maker, and the third output is from the sync output of the first sequence generator. At this point, we will add noise to the channel section of the experiment. Students must make measurements and set the potentiometers to the appropriate level, as well as adjusting the potentiometers on the decision maker and frequency counter. To reset the signal, hold in the reset button on the line code decoder, then the reset on the line code encoder. Release the decoder's reset and then the encoder reset, then press reset on the frequency counter. The frequency counter screen should be blank if there is no noise added. Turning the bottom potentiometer of the adder module clockwise will add noise to the signal. The waveform looks more unstable on screen as noise is added. The screen of the frequency counter will begin showing the number of errors as they are counted. To get an eye pattern of what you are looking at, simply remove the patch cord from the sync of the first sequence generator in the transmitter section, and repatch to the clock input of that same sequence generator. Adjusting the potentiometer of the baseband channel filters module will give you slightly different eye patterns for each signal encoding option, and of course, TIMS has several different encoding options as well, including NRZM, RZAMI, and die-code. Looking at the TIMS transmission model brochure, we can see what we have just done. We have modeled an encoder, skipped the modulation, a channel, skipped the demodulation, and then the decoder.